Hey there. Ever wonder why some AI models master new tasks effortlessly while others stumble? It's all about generalization, the art of learning from examples and applying that knowledge to the unknown. But how do we actually measure this? Today, we're diving into a groundbreaking study that uses math, topology, and stability theory to decode why some models outperform others. Let's start with the basics. Imagine training a neural network to recognize cats in photos. You show it thousands of images, and it learns patterns. But how do you know it won't fail on a new photo? That's the generalization gap, a major hurdle in AI. Traditional methods rely on tricky math like mutual information, which measures how much a model's predictions depend on training data. But here's the problem. Those calculations are messy, especially for real-world algorithms like Adam. They're like solving a puzzle with half the pieces missing. Enter topological generalization bounds, a fresh approach that swaps complicated math for a simpler idea, the shape of a model's learning journey. Think of it like tracking a car's path on a road. The car doesn't just care about its final destination. It's the route, the twists, turns, and hills that determines how smoothly it drives. Similarly, a model's trajectory through parameter space, the mathematical road it travels during training, holds clues about its ability to generalize. But here's the twist. Earlier methods still relied on that tangled mutual information. The breakthrough. Researchers found a way to eliminate those terms entirely by focusing on algorithmic stability. What's that? Picture a car that doesn't swerve when the road gets bumpy. A stable algorithm produces similar results, even if the training data changes slightly. They defined a new concept, trajectory stability, which measures how robust an algorithm's path is to small perturbations. By linking trajectory stability to topological data analysis, TDA, the math of shapes and structures, they derived new bounds that depend on just two things. 1. The topological complexity of the model's training path, like how twisted or simple the path is, and 2. The stability parameter of the algorithm itself. And here's the kicker. Their experiments show that as training data grows, those TDA terms become increasingly important. This explains why earlier studies saw strong links between topological measures and generalization. Those terms aren't just noise, they're the key. But let's dig deeper. Traditional metrics like Rademacher complexity, a measure of how well a model fits random noise, only tell part of the story. A low score suggests good generalization, but it's like checking a car's engine without testing its handling. That's where stability comes in. Imagine training a model on a dataset, then tweaking a single data point. If predictions change wildly, it's unstable. But if it stays steady, that's a good sign. Stability is like a model's calm under pressure. It tells us how reliably it'll behave with new or slightly different data. Now here's the game changer. Researchers combined Rademacher complexity with stability checks to create tighter generalization bounds. Think of it as a safety net that's both snug and flexible. This means we can trust models more, especially in real-world scenarios where data isn't perfect. It's like having a GPS that updates in real time, instead of relying on a static map. Of course, there's a catch. Their method works on average, not for every possible dataset. Some older techniques promise guarantees for all data, but this approach shines in practice. Why? Because it accounts for how models actually interact with real-world data. No more theoretical wishful thinking. Let's get technical without the jargon. The model's error, how wrong it is on new data, depends on two things. 1. Complexity Rademacher score, and 2. Stability, how much predictions change with data tweaks. By optimizing both, the researchers proved that error grows slowly as data scales, like a car accelerating smoothly instead of lurching forward. It's a big deal for applications where data sizes are huge, like self-driving cars or medical diagnostics. The experiments back this up. When tested on models like vision transformers and GraphSage, the new method outperformed older techniques in real-world scenarios. It's not just theory, it's a practical tool for building smarter, more reliable AI. So next time you see an AI model improve with more data, remember, it's not just about quantity. It's about finding the perfect balance between complexity, stability, and real-world smarts. Thanks for watching, stay curious, and we'll see you next time.